Okay, welcome everyone to the PD reading seminar organized by Professor Hiroyoshi Mitake and myself. So today we have Sarah Strikwerda, who is currently an RTG postdoc at Wisconsin. She's going to give a talk on controlling discrete semilinear wave equation towards flux. Please, Sarah.
All right. Thank you so much for the introduction and for having me here tonight, or in the morning for some of you. Today I will be talking about controlling discrete semilinear wave equation toward flux. So we have a nice wave in the background, although we know that it's not really water waves that we'll be talking about today. And so to start out with, we will talk about the equation. So the equation that we'll be thinking about is actually going to be on a lattice. And so we have this grid here, and we're just thinking about the function values on each of these nodes. And so D and N are just natural numbers, and then this distance is going to be 1 over D. And this is in the picture just when n is equal to 2, but we could do other dimensions as well. And so then really our domain is just this lambda, which gives us all of those points on the grid. And so then we're going to assume that alpha and beta are greater than 0, and then we'll be looking at this discrete Klein-Gordon equation. So we have the typical wave equation here with the WTT minus the Laplacian of W, although this Laplacian is the discrete Laplacian, so it's given by this formula. And it's depicted in this picture where if you have one node, the black node, we're looking at the difference between the function value at that node and the surrounding ones and adding all of those differences up and dividing by the distance squared. And then over here we have the nonlinear part of the equation. And what we want to notice is that if your time derivative is equal to plus or minus the square root of alpha over beta, then this nonlinearity is actually going to go away, because we'll just have this squared and all of these terms will cancel out. And then we also have a control U here as well. And then we have our initial conditions. And so for our control, we're going to say that it has to belong to the set A, which is the set of L infinity functions that are Zn periodic. So we're going to be thinking about this in the periodic case. So these orange sides, this side can be identified with this side, and this top or bottom can be identified with this top. And so we're in the periodic setting, so our control will also be in the periodic setting. And then we're going to say that it has to be less than or equal to some m. If we got rid of this restriction, the problem would be much easier. We would be able to control this equation freely, but we are going to just assume that we're in the case where our control can only have this maximum m magnitude. So why study this discrete Klein-Gordon equation? This goes back a ways. Back in 1953, Fermi, Pasa, Ulam, and Singao they had access to this computer system, and they really wanted to find a problem that would be interesting to solve on the computer system. And so they decided to simulate a vibrating string with a nonlinearity. And what they expected to see from the computer system was that the system would thermalize and the effects of the initial data would disappear. So all of the modes would end up being approximately equal, but they actually observed some very complicated quasi-periodic behavior. So this began a study of people trying to understand what was going on with these different vibrations, and trying to understand these atomic vibrations better. And so there were many studies. One of them looks at Pearsall's lattice, which is actually from 1929, so before this, but there's a relation there. And then more recently, Spahn describes the connection between these types of atomic vibrations to the Klein-Gordon equation. And so there is this relation here. And so our goal is that if we can control this equation, then that could give us some insight into problems of this type. So specifically, we're looking to control the problem into these things called flocks. So we say that this phi, this function, is a moving flock if it has a certain description in space, and then with respect to time, everything's moving with constant velocity. So you'll have a function value at each of these nodes, L, and then everything should be moving at the same velocity. And then specifically for the flocks, we're going to say that this velocity should be plus or minus the square root of alpha over beta because that cancels out the nonlinearity. And then we're going to say that phi is a stationary flock if we don't have any velocity and the velocity is equal to zero, because that would also cancel out the nonlinearity. And for both of these cases, we're going to require that this, for the moving flock and the stationary flock, the condition on what the configuration looks like is that the discrete Laplacian of it should also be less than or equal to m, where m was the maximum on the control. So the questions that we asked were, given initial conditions, can we drive the system to a flock in finite time? And then given an initial condition and a moving flock, can we drive the system to a translation of the given flock in finite time? So the first question, we're just saying, okay, given anything, can we drive it to just a flock? But then once we figure out that out, okay, well, now can we drive it to a specific flock? If you give me a flock, can I drive the system there? And both of these should be in finite time. And then the last one is for the stationary flock. So not only can we drive it to a moving flock, but we can also drive it to a stationary flock in finite time. So those are the questions that we set out to answer. And so to do this, what we did is we took this Klein-Gordon equation and actually looked at it as if it's an ODE because it's discrete, so we can do that. And so here the vectors are going to be of the length of the number of nodes that you have in your system. So they're quite long, but what we notice is that if you think of WTT, if you think of that as the time derivative of the velocity, then we get a similar equation to what we had here. But now it looks like in this form where the WTs are now our velocities, and then we have this control at every node as well. We have our initial conditions, and the derivative of the position should just be the velocity.
Sarah, can you explain again when you put the sort of the compatibility condition of when you try to make it to, I mean, based on exactly this slide, like when you,
Yeah.
yeah, yeah.
Yeah, so why did we say that we want our flock to satisfy um, this condition right here? And so if we look at this equation, then we'll notice that we this term will be canceled out if we're looking at a stationary or a moving flock, but we'll still have this term. And if we want our velocity to stop moving, then our control is actually going to just have to be the negative of whatever this term is. And so for that configuration of the different nodes, we want the discrete Laplacian to be less than m so that the control can cancel it out and still satisfy the condition of the control being less than m. Yeah. Is that the answer?
Yeah, thank you.
Yep. All right. So here we have a theorem where we can actually drive the system to a flock under the condition where m is going to be greater than this value right here. So if m is greater than this, and we have some initial data, so we have an initial configuration, it can be whatever you want it to be as long as we're sticking to that periodic case, then there does exist a control satisfying this condition of being less than m, such that the solutions to this system are of this form. So this is a moving flock because we're going to have a constant configuration plus this capital T times a V bar is also just going to be constant in time, and then we'll be moving with this V bar velocity, and that V bar should be that square root of alpha over square root of beta like we talked about. So here we wrote the positive one, but you could also do it if it's the negative one. Um, and so in particular, we are going to have that W looking like the moving flock. So to prove this, what we do this in steps. So you're given an initial configuration, and in these pictures here, what I'm drawing is the dots are supposed to represent the values at each node. And so really those values are just real numbers. It kind of looks like they're in R2 based on my picture, but that was just to spread things out to make it uh, more clear to the eyes. But all of these dots actually just represent a number in R. And so we have some initial configuration, a value at each of the nodes. And then what we want to do is drive the system to a point where all of the velocities go towards zero velocity. And then once we're towards zero velocity, we'll actually be able to get to a point where the flock has exactly zero velocity. And once we're at zero velocity, then we can drive the system to our new desired flock that has this constant velocity for each of the points. So you'll notice that the points, they do move around a little bit. The configuration doesn't stay the same because it's now just a generic flock. So for this theorem one, this is just any flock. Okay, so to do the first step, what we use is the Lyapunov function. So we're looking at this capital V of t, which we'll call the Lyapunov function. So we have this right here, has the energy in it. And our goal is to drive this capital V of t to zero because that's also going to drive this V of L towards zero as well. And so if we look at this, the time derivative of this capital V of t, then just calculating it directly, we get this right here. And then what we can do is plug in what we know V dot should be equal to based on our equation. And so now we have this expression here. And then we notice that this term paired with the VL is going to cancel out a little bit over here. And so, oops. So we're going to be left with just these terms. And with these terms, then we can um, we can just rewrite this so that we have the norm of VL squared, and then we have this ULVL. And so now we can see that if we choose UL properly, we should be able to drive this towards zero. But actually, we do want to make sure that we're not just driving the time derivative towards zero because we don't want to have this case where the velocity goes towards zero, but the function actually doesn't go towards zero. So really, we want to show that the velocity of this capital V is either greater or is either less than some constant, or it's even good enough if it's just less than some constant times the VL of t to the n. And then we can show that VL of t goes towards zero, and that's what we want. So this is the V of t. And if V of t is non-decreasing, then that means that the VL squared should be less than or equal to 2 times the original capital V. And also this other term should also be less than or equal to 2 times that original V. That's just based on this expression that we have right here. And so that means that this VL dot should be less than or equal to C plus some alpha times C plus UL because we know that our VL dot is equal to this expression right here. And so if we have bounds on VL and we have a bound on this term right here, then we have a bound on this right here. And so what these constants are depend a little bit on our choice of control. Okay, so if we have this V dot is less than this, which is less than zero, we can show that the limit of VL is actually equal to zero. We can do this by a proof by contradiction. So if you assume that this is not the case, then there does exist a C naught greater than zero and an index L. and a sequence of times tk that go to infinity such that the velocities are greater than some c naught. So you have these different points for at these different sequence of times. But we actually know that this VL prime is less than or equal to C. So that's going to mean that we can only get up to this point and decrease back down from this point so fast. We can't do it instantaneously because we have a bound on the velocity. So that's going to mean that there exists a tau such that VLT is greater than C naught over 2 for some interval around each of these TKs. But then that means that V dot of t is going to be less than this value, this C2 over 2 to the n of C naught to the n. And that's going to be less than 0 for all things in this interval. And so if that's true, then that means that the limit of v of t should be negative infinity because this is going to keep happening at all of the intervals and the tk's go off towards infinity. But then that will contradict the fact that v of t is greater than or equal to 0. We can see it's greater than or equal to 0 because these are positive terms. And so if we can show this, then we'll be good and we'll have that the limit of VL of t equals 0, which is what we wanted. We said that we wanted our first step was to get us from our original configuration to a point where the velocities were close to 0. And so what we did to do that is we used a control that was inspired by this other paper. So it's not necessarily the most uh, direct one, but it has some advantages for if this were an actual control problem. So what I mean by that is we're going to define this UL of VL to be equal to these different functions on different time intervals. We could have just used negative MVL over the magnitude of VL at all of these points, but this one has the advantage of being 0 if your VL is big enough, which if you have to pay to use your control, it would be better to not use your control if you don't have to. And so that's why we designed the control like this. And so basically what we have here is we have a gamma that's going to be greater than the max of these things. And then we'll have an A1 and an A2 based on that gamma. And so when t is in this interval for some t naught that we'll define later, we're going to say that our control is 0 if VL is greater than or equal to 2a squared. So remember, this is our velocity, and so if VL is large enough, then this term, this negative term, is just going to drive the time derivative towards it's going to make it negative. So it's going to drive the system towards 0, and we don't even have to use the control. But as soon as we get close to this A2, we'll want to start using the control itself. And then when we're between A1 and A2, then we'll have this control. And we can see that that's going to, if we plug in the ULVL in here, then that's going to make this term equal to negative m times the norm of VL. So that is what's going to force this to decrease. And then here we can have negative m V1 over A1. So in order to really show that all of this works, we kind of need this key inequality showing that our velocity, our v dot, is smaller than what we want it, smaller than a constant or smaller than a constant times VL to some power. And so first of all, we're going to think about this interval or this set of nodes in lambda bar, which could change depending on the time. And that's for the VLs in A1 and A2. So in this case, we said that UL is equal to this negative MVL over the magnitude of VL. And so when I plug that in, I get negative MVL. And then when I look at what the actual derivative is, it involved this term, and I can see that that is now going to be less than VL times this term right here. And then that's going to be less than VL times this constant. And this is where it is necessary for us to assume that m is greater than this constant right here. So here we need this in order to show that we actually have our v dot L less than a constant on this interval. And then we can also look at the set of nodes where our VL of t is less than A1. And so in that case, this was our control. And similarly, we can say, well, UL VL is equal to this. And then we can say that our A1, if we recall that it was equal to this quantity right here, then we can see that and we know that our gamma is equal to this, then we do have that alpha is less than m over a1. So then this quantity right here is going to become, because alpha is less than m over a1, we can say that this is less than or equal to beta times VL to the fourth. So we get that this V dot L is less than the constant times VL to the fourth. And then for our last interval, or not really interval, but set of nodes, then we have that our VL of t is greater than A2. In that case, we used these two different controls. And what we notice is that the ULVL is going to be equal to 0, or it's going to be equal to this expression here. And so then this is going to be less than 0 in that case, though. And then we also see that since A2 is equal to this gamma times the square root of alpha over the square root of beta, and that's greater than the square root of alpha over the square root of beta, then what we see is the other part of the derivative, this nonlinear term, is going to be less than this because we said that our VLs were greater than A2 squared, or they were greater than A2, so we have that. And then what we have is we can plug in this expression where now our beta A2 squared can be replaced with this gamma squared alpha. And then we can also use this quantity on the A2 again, the fact that the VLs are greater than A2. And so then this is equal to this negative constant, which is less than 0. So adding this up, our total velocity for the Lyapunov function is going to be less than the sum of these three cases. And this is enough to say then that the limit of capital V of t is going to be 0, which then also means that the limit of the L of t is equal to 0 for all L in the grid. So a useful fact in step 1 is that this is our Lyapunov functional, and the ODE satisfies the ODE solution is going to satisfy the limit of this being equal to 0 when the UL from step 1 is used as the control because this is going to 0. So this term will also go towards 0, and it'll be useful that is small. And so we have that the XL dot is equal to VL, and that is greater or less than or equal to 2 times the initial V of 0. And so that means that these XL are Lipschitz. And we know that there is not an infinite limit. So we assume that there's a sequence with a non-zero limit, but then we can use the ODE equation to show that the velocity would not be able to converge to 0. And so that means that the sum does actually converge to 0. Okay, so that's step 1, where we have the system and then we drive it towards a system that is close to having 0 velocity. And from step 1, we have that the discrete Laplacian of where we're at this t0, which is at the end of step 1, is less than epsilon, and that the VL of t naught is less than epsilon. And so we can define this t1L to be equal to t naught plus 1 over epsilon VL of t naught for each of these L's. and the T1 is going to be the max of all of these T1Ls. So we have a different time for each of the nodes, and then we can take the max of them. And so at the end of T1, we hope to be done with step 2. And so for step 2, we define our control UL of t to be equal to VL dot of t minus the sum of the XL prime of t minus XL of t over h squared, and then minus this nonlinear term as well. And so what we notice here is that this UL, if I plug it into the equation, then um, the equation will just automatically be satisfied. So here I'm really just saying that we have a control that is going to drive the system towards this VL and this XL. So what we did is we kind of worked backwards where I knew what I wanted. And so I wanted to get this VL to the place to this spot where at the end I was going to get rid of the velocity completely because the goal of step 2 was to drive it to a stationary flock. So I want to get rid of the velocity. And so I knew I wanted to get here. And so then to get there, because XL is just satisfies the fact that XL dot equals VL, I can say that this should be XL. And then if I plug them into the equation, then I get that this is UL. But the main thing that's left to do is we actually want to show that this UL is less than M because we said that we really wanted our controls to satisfy this bound where UL is less than M. And so here, one important note is that if I look at XL of t minus XL of t naught, then just from this definition of what XL is, I can see that that's going to be the magnitude of VL t naught times T1 L minus T naught plus this term here. And so this is going to be less than or equal to this term. And we remember here that VL of T naught is going to be less than epsilon. So, and that's because in step 1, we got close to a stationary flock. So this is now less than 2 epsilon. And then, so our goal is to show that this UL is less than M, and we can say that after this set time, our UL should just be equal to this term because after this T1L, then we have 0 velocity, so the nonlinear term goes away, and this is all that UL is. And because our XL of t minus XL of t naught is less than 2 epsilon, then this sum right here should be less than epsilon. And then before the T1L of UT, before this point, then our UL actually has more terms here. And we can use the fact that XL is equal to this and VL is equal to this to plug VL into this equation. And using the fact that VL of T naught is less than epsilon, we can also show that even before T1L, UL will still be small, and so we'll satisfy this condition of UL being less than M. And so because we have a control where UL is small and it drives us to a point where the velocity is 0, we can move on to step 3. So step 3 will define T2, which will be the endpoint, the time we end step 3. This is going to be equal to T1 plus this constant right here. And so to define UL in step 3, we define it in this way, where I have to tell you what W is yet, but again, we're just trying to cancel out the terms on this side of the ODE. And then the W I'm going to define is going to be equal to V bar over T2 minus T1, which is equal to M over 2 based on how I defined T2. And then we're going to define it as 0 once we're past T2. And so in this case, if I use this as the control, then what happens is we get our velocity to be m times t minus t1 over 2. And then for t between T1 and T2. And then our VL of T2 is going to be this square root of alpha over beta. And that's what we wanted. That was our goal, is to get to a flock where we have this velocity. And what we notice then, so our second goal then is to make sure that our control is actually small enough. And so one thing that we notice is that this right here is also going to be equal for all of the t's in this interval. It's going to be equal to whatever the discrete Laplacian was at t1, because all of the points are moving with the same velocity. And so this is going to be very small. And then we also notice that the nonlinear term is going to be small as well, because we have that, we can show that it's less than or equal to this value, and that is the value that we assumed m is bigger than. And then our UL of t, just using the triangle inequality now, that's going to be less than this m over 2, but then this is less than minus m. So we have this whole thing is less than or equal to m over 2. And then we said this was also going to be less than or equal to m over 2. It's actually quite small, less than epsilon. And so the whole thing is going to be less than m. And so we have what we wanted. And so that is the end of our proof for theorem 1. We've shown that given any initial configuration, we can drive the system to a moving flock. But then theorem 2 says that we actually want to say that given a flock, we can get the system to that flock. And so here we're still assuming this condition on m. And at the end, we're saying that this ODE is satisfied by something that satisfies this moving flock that was given to us. And so for this proof, what we want to do is say, okay, well, if we have an initial configuration, we know that we can drive the system to a close moving flock. And that was theorem 1. To prove theorem 1, we showed that given any initial configuration, you can drive the system to a moving flock. And in that proof, we noticed that that flock was close to all of the values, that the nodes were all close to each other. And so then we can say, okay, well, given that close moving flock, we should be able to drive the system to a constant moving flock. So we already know these points are close, so let's all make them the same. And then from there, we can drive the system to the desired flock. And so if we let t naught be the time at which UL of t from step 1 has driven the system to this point, where we have this closeness, and we have the small velocity, then what we can do is define this y bar to be some kind of average of all of the values at the xl's. So it doesn't really have to be this average, but if you want to do things in an optimal way, which this is not optimal control, so there's lots of ways we could make it more optimal, but it's best to choose something that is kind of in between all of the xl's. So we can let T1 be greater than T naught, and satisfy this equation right here. Noticing a typo, this should be T1 minus T naught. And so what we notice is that we have T1 minus T naught cubed on the bottom, and the highest power of those on the top is squared. And so we know that this whole thing is going to be going to 0. So we can choose a T naught or a T1 where this whole thing is less than m minus epsilon. And then from that, we can define our UL of t to be equal to, again, we're just kind of taking the parts of the equation that aren't UL. So of course, UL has to be equal to this for the system to be satisfied. So we're kind of working backwards. And the UL is going to be equal to that when the VL is equal to this V bar plus this equation right here. And so we notice that if you plug in T1, this term goes away. So at some point, we're going to get it to be just this V bar. And then the XL has to differentiate to be VL. So that ends up being this expression right here, where at the start we're at XL T naught. And so um, we want to show that this control is going to be less than m, but we can do that because this is less than epsilon, and this part is less than epsilon. And looking at what our v dot is based on this, we chose our t one to be large enough where this expression was less than m minus epsilon. And so that is going to tell us that when I differentiate this, this VL is going to be small enough. And so that's where we're going to get this UL to be less than M. And so we have this control that is going to complete step 2 and bring us to a place where we have all of the XLs are going to be the same thing. And then our V's, L's are all going to be V bar. So then we can move on to step 3, and similarly, we'll let T2 satisfy this expression where we want this to be small enough, and it can be small enough because we have this cube term on the bottom, where now this is going to be less than m minus the discrete Laplacian of the given flock. So we said that the Laplacian of the given flock had to be less than m. So this is still a positive number. And so if the Laplacian of the given flock is close to m, it's going to take us a while for this to get small enough. But we can still get there in finite time since this expression does go to 0. And then we'll define our UL similarly as we just want the system to be satisfied. And our VL is going to be now this V bar times this expression here. And so basically we are starting at just having the velocity being v bar, but we're going to leave that a little bit so that we can allow the different terms to move around to get to the new configuration. And then at the end, we want to go back to v bar. And that's what this term is allowing us to do. So we see this difference of where it started and where we want it to go in this expression. And then our XL of t is going to be, again, this XL of t1, so where we started, and then these other terms where we notice that if we differentiate XL of t, we get VL of t. And then we also notice that if I were to plug in t2, then I would have, if I plug in T2, then I actually am going to get this XL of T1, but then I'll end up subtracting XL of T1 and I'll get this X bar of 2L, and then I'll also have T2 minus T1 times V bar as well. And so as long as we can show that the control is less than m, then we're done with that step because we've landed at the configuration of the given flock. And we can do that because of this assumption that this is less than m, and that so if we plug in the XL and the VL and the VL dot into this and then use this condition, then we'll get that UL is less than m. So with that, we can move on to theorem 3. So in theorem 3, we want to drive the system to a particular stationary flock. So similarly to before, we're given a flock, but now it's stationary. So our V bar is just going to be 0. And we still have this condition on m, and so we still have the condition on the Laplace that it should be less than m. And then we say that U is going to be part of this class that's less than m, and we can find a solution to this system that after some finite time, it actually goes to having, oh, this should be 0 here, so 0 velocity and this given configuration. So to do that, we drive the system, so we have some initial configuration. we drive the system to a close stationary flock. So we did that at the end of step 2 in the proof for theorem 1. And then from there, we can drive the system to a constant stationary flock. And then from our constant stationary flock, we can drive the system to the desired flock. Um, and so I'm not going to give the details of the proof because they're the same as before. We designed these controls by just looking at which control is going to satisfy the system, and then just choosing T large enough so that the control is actually less than M. But I do want to connect this to optimal control. So in this process, we have designed these controls. They're called feedback controls, and they do drive us to where we want to go in the system, but we're definitely not claiming that they're optimal. They weren't designed to be optimal. And to do that, we really would want to think about how we can connect this to the theory of optimal control. And right now, in this setup of the ODE, we have what's called a non-local ODE. So we have x dot L of t is equal to VLT. That part's fine. But then in this VL dot t, we have that this is equal to this sum. And so the time derivative at the elf node is dependent on its neighbors. So that's what makes it a non-local ODE. And of course, we could just rethink the way that we're looking at this problem by defining this x1 to be xl. So this is a vector where it has an xl for all of the l's in the lattice, and then x2 is just a vector of all of the velocities in the lattice. But what we notice here is that x is now going to be x1 and x2, and so that is going to be in R2D to the n power, so very large. And then we have that we could write now this non-local ODE as a local ODE, where now we have this x dot is now going to be equal to b tilde of xw, where that is just going to be b of x plus 0w. And so here, this b of x is going to, the first components are just going to be x2 because that's representing the fact that x1 dot is just equal to this x2. But then after that, we have this expression. So this b of x now has all of these terms in it as well, representing this equation. And so in this way, we now have a local ODE. And once you have a local ODE, you can look at the Hamiltonian. So typically the way this optimal control theory goes is that the target is now going to be gamma. So it's the x's where this discrete Laplacian is less than m, and x2 is going to be, for all of the l's, is going to be plus or minus the square root of alpha over beta. And then the Hamiltonian is going to be h of xp. That's just going to be the soup of our control over our controls of negative b tilde xw dotted with p minus 1. So that looks like this. And then if ux is the minimal time it takes to start from a given state x and reach gamma, then u is a viscosity solution to this equation right here. And so we could figure that out. We do know that u is finite because we showed that given any initial flock, you can reach something in this set in finite time. But to actually solve or really study this ODE, that would be challenging because this ODE is in dimension r to the 2d to the n power. And so, yeah, just that's just a lot of dimensions to really gain anything from this Hamiltonian. So that kind of explains why instead of looking at this optimal control, we were looking at this feedback control and just designing the control so that we could reach flocks. So we've shown that U is finite, but we could do more to try to study this equation. But as you can see, that would be a challenging endeavor. And so with that, I just want to say that we can do that. So that's one future question. But other things that we have been thinking about is what would happen if we remove the periodic boundary and we just study the problem on all of Rn, but maybe with compact support to begin with. So if we say that the initial configuration has compact support, as soon as we let time continue, what's going to happen? Or if we like perturb it a little bit, like how is that going to spread out into all of Rn? And so that's one thing that we want to look at a little bit more. And then another thing that we could think about is here. When we looked at this nonlinearity, we noticed that the square root of alpha over beta made it go away. But with any nonlinearity, if it has some zeros, we could potentially do a similar process and think through how we can control it and drive that system towards flocks. So that could be another thing that we could look at for different physics applications as well. So with that, I would just like to thank Hung and Minbin for collaborating with me on this and bringing this problem to my attention. And also thank you to Hung for the invitation to give this talk. And then I have some references, of course, our paper, and then yeah, some other ones that I mentioned today during the talk that you could check out as well. So thank you very much.
Thank you, Sarah. Great. So exactly, you know, on time, we have time for questions and comments. Uh, any questions or comments? Actually, we have Bing here. So Bing here. Can you also, so I mean, the point is actually that Sarah and I were looking for some other new direction to do, right? And then Bing was the one who suggested, looking into this direction. So can you make some comments, Bing?
So thank you, Anh Hưng. So the problem is motivated so I want to explain the physical meaning of the model, right? So for this model, so the origin of the model is the work by Payers, where he looked into the vibration of the wave inside a solid material. So inside a solid material, you have lattice. So atoms are in the lattice and they are vibrating. So if one atom is vibrating, it's going to affect the neighboring atoms. So you have the nearest neighboring relation. And so what Payers was looking is that he looked at this the vibration of those atoms inside this solid material, and this can be modelized by the wave equation. And so later on there was also several works on the harmonic oscillator. So you put a lot of oscillator and you put that into a chain, and so one object in the middle will interact with the two objects next to it. So that you can also modelize by a discrete wave equation. So the meaning of this control is to put something onto those systems. Say you have a chain of oscillator and you put a control there and
Sorry, Bing. So, Sarah, can you go to the exactly the slide of the equation so that, I mean, for us, we are used to it, but for some of the
Mhm.
others, well, maybe the discrete equation that you have there, can you go to that slide?
Yep.
Yeah, sorry, Bing, and then you can say.
Hmm. Here we go.
The very first one. I mean the
mm, may this
yeah,
one?
yeah, yeah.
Yeah, so this is the lattice that pair was looking at. You have L that is interacting with L prime, all of the L prime. So it's nearest neighboring interaction. So in the lattice, normally for solid uh, material, the atoms are like this. They are they're on a lattice. So when so when one atom is vibrating, it's gonna affect the one that are next to it. And so you can modelize that by a wave equation. And the next model is you put a lot of oscillator and you put that into a chain. So one oscillator is going to be like this. But if you put them together, it's going to be interacting um, in the nearest neighboring way. And so one famous experiment is the Fermi-Pascal-Ulam Xinhu. So in this experiment, what they expected in the numerical experiment, what they expect is that when in the long term, everything will be thermalized, meaning that they're going to be stable and go to equilibrium. But what they see is something chaotic, and they don't understand why. And the thing is still open. So our point is to put a control somewhere onto those points of the oscillator or the lattice to control this chaotic behavior. And then this is what the model. This is the meaning of the model that physical meaning of the model that we are working on.
Yeah. Let me just add one more point that in fact what is interesting here is you can think about is a discrete approximation of the wave equation too, right? I mean, one of the things that people see is that for the wave equation, normally for the continuum model, you have a finite speed of propagation. But for the discrete one, you can think about that as sort of like a Taylor expansion of the wave equation. And when you do Taylor expansion, the discrete one, the difference from the discrete to the continuous one, you're going to have the fourth order terms coming in. So what is interesting is that in this case, for the discrete wave equation, you don't have finite speed of propagation. What it means is that you just do, the vibration of one atom at one place, and it's gonna, you know, affects everything, at infinity. And like what Sarah mentioned, in this case, when we assume everything is periodic, then you have finite number of ODEs. But the moment you get rid of periodicity, that is really interesting because you have infinite system of ODEs. It's and this kind of discrete to continuous approximation that we also see, I mean, in other works like with Yu-Ming Po here or some others, it's really interesting. Yeah. Anyway, that was a long chat. Sorry. Any questions or comments?
Can I ask a question?
Please.
I noticed that there is a condition like m needs to be greater than some combination of alpha and beta. I'm wondering, is this necessary or just technical?
Yeah, let me find it. Yeah, so right here, for example, um, when you use this control UL, and then uh, we're looking at the Lyapunov and trying to show that it goes to zero. And so we want to show that this V dot L is going to be less than some constant. And so this ULVL is going to be equal to negative MVL. And then when we plug in here, what we can see is that this is the case where VL is in A1 and A2, in between A1 and A2. But really what we notice is that I have this VL squared, so I could just put the VL here and then put alpha times VL minus beta times VL cubed. And then if you just look at this cubic right here and think about like where's the maximum going to be? I mean, that's just a calculus problem at this point. And the maximum is going to be this value right here. And so for some VL, this will achieve this point. And so then that means that this whole thing will be less than VL to times M. And so then when we plug this in and this in into the derivative of v dot L, then we get this. And so we can see that to say that this is less than M, we need that assumption. And also here to get that, that is equal to a negative C2. Yeah, that comes from the fact that this is less than VL to the M. And so because this does actually achieve its maximum, we needed that M. And then if we look at the control itself to think like, okay, well, maybe we could use a different control, what we see is that we're trying to get this V dot L to be as small as possible. And we really, it works out well when this UL is some constant times VL. And this is the maximum constant times VL that we could use for UL to ensure that UL is less than M. And so there's not really much we can do here except assume that M is greater than that value.
Okay, so I guess you convinced me that if you want a pointwise decay of the Lyapunov function, this is probably the best. But maybe there is some, maybe you give up pointwise decay, but maybe there are some global, I don't know, some global ways. But yes, you answered my question.
Yeah,
Thank you.
no, that is a very good point, Paul. I think that there was also another direction that you can make sparse control, right? So what Sarah said, that if you do pointwise control, you really need uh, U to be, I mean M to be greater than that much.
Mm-hmm.
But now if you do sparse control, like what being said, right? I mean, you don't put the control on all
Uh-huh.
the atoms. Let's say you only do it on the odd atoms, right? I mean, you do it sparsely.
Mm-hmm, mm-hmm.
Just randomly put some control somewhere. Then can you
Yes.
drive it down? So you need to use some more global quantities instead of
I
point.
see. Yeah.
Yeah.
So was someone did this, or someone did something like this, or
Someone asked exactly that very intuitive question, like what you asked. Can
oh, I
you
see. Someone
specify the
gotcha.
control? Yeah.
Gotcha.
Yeah.
Thank you.
Great. Can you go to the optimal control problem, Sarah? I just want to explain very quickly to the young audience.
Oh, the optimal control, the Hamiltonian.
Right. Yes, this one. So very quickly for the younger audience, I mean, this is kind of I mean, although it looks simple, but this is kind of a big deal these days that people try to do something called the master equation. So you look at the non-local equation that Sarah mentioned. So VL is not local because it depends on the nearby neighbors. But there's always a method for you to make the problem local. To make it local, meaning you just collect all the variables and you just dump them in one master variable, which is the big X that Sarah put there. When you dump everything together in one variable, then of course your equation has to be local, right? Because you collect everything and you see that the bx Sarah put there, the non-local terms appear in the second slot. So it's really messy, but because it's x itself. So then you have the local equation that x dot equals to bx plus 0 w, and you see that the control only appears in w, right? So it's exactly that you are, so this is the same example that Jack gave in the colloquium on Friday, that you have w is less than equals to m, so you have the strength to drive your system somewhere only in the second slot. And can you go to the Hamilton-Jacobi equation, Sarah? I just want to make, and this Hamilton-Jacobi equation, this one also looks like the G equation that Jack presented. Because you have that the second term is exactly the Icono equation coming from your control. but B is your vector field. Yeah, so it certainly appears that it's related to the G equation. We have not go deeply here, but I guess there's something. I don't know. Yeah, but it's really related to exactly the thing
That's
that
very nice. Yeah, thank you.
yeah.
Yeah.
But this is a more non-cursive because
Yeah.
this is gradient. The second term is gradient on x2, right?
Yes, yes. So I
This
mean,
is
it's not exactly the G equation that
Mm.
Jack and Yifeng has a big program on, right? But I mean, it's kind of only cohesive in and not exactly even cohesive, right? It's only control on the second slot, like what Hiro mentioned. Uh, but I think that no one, I mean, we have not go deeply in this Hamilton-Jacobi problem. There must be something deeper than this, but we have not tried. And the B looks kind of complicated. Yeah. But it's surprising. I mean, it's related to G equation. So
Yeah, indeed. Thank you. That's very nice. Yeah.
yeah, thank you, Jack. Any other quick questions for Sarah before we end our formal discussions? Okay, if not, then let's thank Sarah again for a great talk. Thank you, Sarah. So let me